All right, we're going to look at integrating over the plane when we don't have rectangular constraints. So if I get my axes drawn here, so there's my z-axis, there's my x-axis, there's my y-axis. And so if I'm looking at a bound, but the bound is not a rectangle. So we'll say in the xy plane, we have a series of constraints, and we're moving. Let me change my orientation here. All right, we have constraints here, and these constraints are limiting the boundaries of our xy, and then we have some function z that creates a surface above this. And so, right, we have this oddly shaped surface that has these indentations from the xy plane on it, right? And so this here is a function of x, this endpoint, and this here is some function of x, a beginning point. And so we could create a wedge that its length is the difference between the two functions, and its height is the height of f of xy. And so we can create an area element, some area that's a function of x. And so this area function of x can be these little vertical slabs coming across. And so we have some area that's a function of x that has its length as being the difference, that its length element is from here to here. And so we're going to integrate across the length the height of our function. And so we're going to integrate from the lower function of x to the higher function of x. And we'll do that across dy. So we're integrating across y because we're parallel to the y, and we make these little area slabs. Well, if I want my volume then, I'm going to take my area slabs and I'm going to integrate them from a to b in x. I'm going to go from wherever my starting point. And so I can do a to b of some area element in x dx. Well, this integral slips into here, and so I have my volume element from a to b, and then in from y, which is an endpoint that will make a function of x, and some y endpoint that will also make a function of x. And then we have our z as a function of xy. We integrate y first and then x. And so we can make our constraints non-rectangular. We can have a element in here that's constrained by a function or two functions. And we use these functions to make our bounds of the inner integral. And what it ends up doing is it ends up converting variables. We take y as a function of x, and when we integrate through here, our area will be just a function of x. And that leaves us with a singular integration in x to finish. So this double notation, we can have bounds that are functional. It also, right here, I was integrating with y to get my area element. We could change our orientation. whoops, that's Z up here, and this is X hat. So, and we could be integrating a function that's X as a function of Y with our some Z function up here, some cap above all of this. And so we still have Z as a function of X, Y. But now we want to move from H as some function of Y, H1, and H2 as some function of Y. And so we would integrate X first, moving from in the X direction, and then in Y. And so we could move from some C to D in Y, f of x, y, and from x equals h1 as some function of y, and x equals h2 as some function of y, and we'll integrate from dx to dy, and we'll still get a volume element. This lets us write Fubini's theorem in a strong form. So we'll no longer have rectangles constraining us. So we'll let f of xy be continuous on the region R. And now we'll have two options. If R is defined by A is less than or equal to X less than or equal to B, and some function of X is less than or equal to Y, which is less than or equal to some other function of X, which we'll call G1 and G2, with G1 and G2 being continuous, on the interval A to B. Then our double integral across the region, f of xy, integrated across some area element, will be the integral from A to B, integrated. Now your book doesn't put the x equals here. Will just be integrated from some function of x and some other function of x, f of xy, dy dx. And then in the second condition, if the region is defined by c is less than or equal to y, less than or equal to b, and h1 of y is less than or equal to x, which is less than or equal to h2 of y, with h1 and h2 being continuous on C to D, then in our volume integral across the region, so our integral across the region of f of x comma y on some area element is equal to the integral from C to D of h1y to h2y of f of x comma y dx dy, and our order of integration changes. So Fubini's theorem works even when we have boundaries. And this works no matter what our variable structure is. If we have some function of f of u and v, then an u could be from some p and q, and then in v would be from g1, some function of u, to some other function of u. And then you would have fu v dv du. And if you change the order of integration, then you would have v is equal to some p to q, and then some h1 of v, h2 of v, and you would have fu of v du dv. So that would work for any generic function. And I'm going to move my tablet around, my hands kind of cramping up as my thing goes through. We're going to do some examples of these, and we're going to see that the hard part is finding the regions to integrate across.